going to continue solving equations using a matrix equation, or a system of equations using a matrix equation. So what we have now is a 3 by 3 and a 1 by 3. So we have 3 equations, 3 unknowns. And just keep in mind, this is just another method that works for solving a matrix. So what we want to do is find our inverse. Of course, this is just a little more tedious because it's just of the size. Okay, so let's see about doing some row operations here. I need to multiply the first row by a half. So that'll get me a 1, 1/2, 0, 1/2, 0, 0. And then these rows will remain unchanged. All right, so I'm going to multiply row 1 by +4. I'm going to add it to row 2. Row 1 does not change. Okay, so what that'll do is get me a 0 here, a 1 here, a 3 here, a 2, a 1, and a 0. So all I did was multiply each element by 4 and combine with the corresponding element in the row that I'm working with. So here I've got a -3. I'm going to multiply it to row 1, and I'm going to add it to row 3. -3 times 1 is -3, and 3 is 0. -3/2 plus 1 is -1/2. I've got 3 times 0, -3 times 0 is 0, plus -2 is -2. I have -3/2 and 0 is -3/2. -3 times 0 is 0, plus 0 is still 0. And then this is -3 times 0 plus 1 is still 1. So now I need to focus on getting these elements into being a 0. So I'm going to multiply by -1/2 and add to row 1. Row 2 will not change. Okay, so I have a product of 0 plus 1 is 1. A product of -1/2 plus a half is 0. The product is -3/2 plus 0 is -3/2. This product is going to be -1 plus a half is a half. Hang on 1 second. -1, that should be -1/2. Okay. -1/2 is -1, so this is -1/2, and 1 multiplied is -1/2. This is 0. Okay. Let me check my work, make sure I'm good here. Okay. So now I want to make this element become a 0, so I need to multiply by +1/2 and add to row 3. So what I'll have then is 1/2 times 0 is 0, plus 0 is 0. 1/2 and -1/2 is 0. 3/2 and -2 is -1/2. 1 and -3/2 is -1/2. And then 1/2 times 1 is 1. 1/2 plus 0 is 1/2. And then 1 times 0 is 0 plus 1 is 1. So now we need to concentrate on turning that into a 1. So we'll use the multiplicative inverse. So this is -1. This one is going to be 1. That'll be -1, and that will be a -2. Okay, these rows don't change. right. Now let's focus on getting these elements to be 0. I'm going to multiply this element, or this row, by 3, add it to row 2, which will not change row 3. This should be positive 1 here. That's a positive 1. So I have 3. This is going to have to be negative 3. So that still zeroes out. That's still, okay, hang on. There we go. Got my signs right, okay? So I'm verifying my work here. Okay, so now let's go forth. This multiplies to 0. This multiplies and adds to 1. Then negative 3 and 3 makes 0. Then negative 3 and 2 is negative 1. This is going to be 3 and 1 is 4. And this will be 6 and 0 is 6. And now we need to focus on that element. We need to zero it out, so it needs to be multiplied. Positive 3 halves, add to row 1. So then this becomes 0 and 1 is 1. 0 and 0 is 0. 3 halves and negative 3 halves is 0. 3 halves minus a half is 2 halves, or 1. Negative 3 halves and negative 2 halves is negative 4 halves, which is negative 2. And then this is going to be negative 6 halves, which is negative 3, plus 0 is negative 3. So your inverse is this matrix here. Okay, so now we're almost done. Woohoo! We've got 1, negative 1, 1, negative 2, 4, negative 1, negative 3, 6, negative 2. And I'll multiply that by my column matrix, which was 1, 4, 0. Okay, here we go. So I have 1 plus negative 8 plus 0. I have negative 1 plus 16 plus 0. I have 1 minus 4 plus 0. So that then is going to be negative 7, 15, and negative 3. So your x coordinate is negative 7. Your y coordinate is a positive 15, and z is negative 3. If you're thinking about an ordered triple, this is just if you need one. Looks just like that. There is our solution. The next one that you have in your notes looks like this. So what I'm going to do is just talk you through it just a little bit. I'm not going to work it. Went ahead and did my A matrix. I just wrote the equation, the A matrix, the variable matrix, and the B matrix. I go through and I find my inverse. Luckily, this one just didn't have any fractions at all. So this one would be a good one for you to try by yourself, and you've got the work. Okay, so then I took my inverse, multiplied it to the B matrix, did my arithmetic, and got my solutions. So you can pause me here so that you can try to work the problem yourself. The last problem we have is a word problem. So we've got a Colorado company makes artisanal dining room furniture. I guess that's fancy stuff. A buffet requires 15 hours for cutting, 20 hours. Now that buffet is a piece of furniture. 20 hours of assembly and 5 hours of finishing. A chair requires 5 hours of cutting, 8 hours of assembly, 5 hours of finishing. A table requires 10 hours of cutting, 6 hours of assembly, and 6 hours of finishing. The cutting department has 4,900 hours of labor available each week. The assembly department has 6,600 hours of labor available each week, and the finishing department has 3,900 hours available each week. How many pieces of each type should the company produce to be fully operating, at fully operational capacity? All right, which is a realistic type issue. So what you want to do first is make your system of equations. So what we're going to do is let X be the buffets, the number of buffets. We're going to let Y be the number of chairs, and we're going to let Z be the number of tables, just out of convenience. And when you choose your system, what we want to do here, we've got a total of 4,900 labor hours. So this is labor hours. This is for cutting. All right, and then the 6,600 is labor hours for assembly. And the last one is labor hours for finishing, like sanding, putting your stain or your paint on the furniture. So notice where those came from. I've got 15 hours available for cutting. I've got 5 out for the buffet. I've got 5 hours for the chair, and then I've got 10 hours available for the table. And if you just orderly go through like that, you can get your coefficients. Up here, I just showed what the matrix equation looks like. So my comment as far as solving this thing, you've got the matrix equation. This one I did with just substitution and elimination, just regular algebra. You've got the Gauss-Jordan method for solving a matrix, which would be eliminating this, augmenting your matrix, and putting the values here on the right of the augment bar. So you've got a variety of ways to solve these kinds of equations. It just depends on what you want. I tend just to go back to the basic algebra. So what I did, and let you practice that, I put equation, the labor equation. Actually, what did I put? This is equation 3, okay? And I put it with equation 1. And then I solved for Z. And then I did the same thing with equation 4 here. And did all my substitution, and I found 60, 600, and 100. This is a word problem, so I think I might go a little further and say that 60 buffets, 600 chairs, and 100 tables, T-A-B-E-L-S. How do you spell table? There we go. So I've got all those, 100 tables can be produced with these particular restrictions. So I'm going to let you work through that one since I have it already here, and I think this will just serve our purpose a little bit faster. So that would be the end of matrix equations.